Good evening. My name is Sarah Thompson and I'm a physicist at the University of York. Welcome. Welcome to the World According to Physics and welcome to the York Festival of Ideas online. Although we're in a different format this year, the festival still aims to enhance York's reputation as a city of ideas and innovation through offering the highest calibre of public events. This 2020 festival has over 60 online events offering an inspiring programme for all ages. And although we miss welcoming you in person, it's a real pleasure to welcome a wider audience. We're expecting up to maybe 1,000 this evening, many from further afield than our Yorkshire region. Now, before we get started, just a few technical notes. If you're watching live, I can see that many of you have already found the Q&A button, but that's where you can write questions. It's available throughout the talk, so you can post your questions at any time, and we'll be selecting some of these to ask Jim a little bit later on. If you've got any technical issues, such as loss of Wi-Fi, you can rejoin the event, just use the original link. And please also remember that the event is being recorded, so you will be able to watch it again. So, to the world according to physics. Just a few words about the format of the event. Jim and I are going to start with a conversation about writing the book. Then he's going to give us a 20-minute talk about some of the ideas in it, but that should allow us some 25 to 30 minutes for all your questions, which are appearing rapidly. So to our speaker, to Jim, Professor Jim Al-Khalili, OBE, FRS, is a quantum physicist, an author, broadcaster, and one of the best known and loved science communicators in Britain. He holds a distinguished chair in physics at the University of Surrey, where he teaches and conducts his research. He's written 12 books on popular science, between them translated into over 26 languages, as well as his first novel, Sunfall. Many of you will know him as a regular presenter of TV Science documentaries, and my personal favourite, the long-running Radio 4 programme, The Life Scientific. So welcome, Jim. It's quite hard not to say welcome to The Life Scientific after that phrase. So the book, I think we have the first question, which is, why did you write this particular book?
Oh, okay. Well, as you say, I've written a number of popular science books, and lots of other physicists have written wonderful popular science books, and a few have come out quite recently. Very often they tend to be, sort of huge, 1,000-page tomes, really explaining the whole of the history of physics and everything we know and how we came to know it. I felt I wanted to sort of cut to the chase. What do we know now? The cutting edge of physics. What are our latest ideas? What have we yet to discover? What are we likely to discover in the coming years and decades? So it was really sort of like a pocket-sized book to bring the lay person up to speed as quickly as possible on some of these really exotic ideas. Some of them very deep, very profound ideas about the nature of the universe, the nature of reality. And it's challenging just to try and find new ways of getting across some of these complicated ideas.
Yeah, so that was one of the other things I wanted to ask you about. The book covers a lot of very, very deep ideas, things that are very complex, things that are very difficult to understand. Some of them you're very, very familiar with, that you're dealing with every day, some perhaps not as much so. But of all those really complex ideas, what do you find the hardest to explain?
Oh, yeah, so ideas to do with quantum mechanics, the theory of the very small. Yeah, so that's sort of my bread and butter. That's what my research has been it throughout my career. I teach it. So I feel, even though quantum mechanics still gives me a headache, as it does everyone, I sort of feel I'm on safer ground explaining it. I guess what I find more challenging is explaining some ideas outside of my field. So ideas in cosmology, ideas about the nature of the universe, how big it is, was there something before the Big Bang, ideas can be very highly mathematical, very highly abstract, that even, you know, the physicists who've been working them all their lives find it really hard to get across. So I'm coming at it as an outsider from, say, something like superstring theory, to pluck an example out of the air without going into detail of what it all means. You know, even someone who spent their life working on superstring theory would find it hard to get across to the layperson what it's about. So it's an extra challenge for me to try and find a succinct way of just getting across the basics, the basic idea. I don't expect people to be experts in this, but just to come away and say, okay, I have an idea of what this is about.
So one of the other things which I was quite taken with was that you said at the end of the book that you know, you'd drawn on some of those interviews from the Life Scientific, and you know, you listed some of the people, and I just wondered whether you thought there were any, because I mean, there's some really, as you say, controversial ideas in this book as well as deep ideas. Are there any things that you've put in there which you think they might disagree with? Are there things where you've written them and you've thought, so and so wouldn't agree with that?
Yeah, probably, because, you know, to give you an example. I'm going to say something about this in my short presentation in a few minutes, but the two leading contenders for a theory of everything, a theory of quantum gravity. You've got superstring theory on the one hand, and you've got something called loop quantum gravity on the other. I've in recent years had the leading proponents of each side being interviewed on the Life Scientific. And so when I interview them, I try and keep my guests honest. You know, I try and sort of probe them, but I'm not there to sort of attack them. But, you know, it's interesting trying to get across, talking about one theory, talking about superstring theory, when I know that someone else has got, you know, wouldn't agree with that. And then I have to jump to the other side and the other person wouldn't agree with it. So because I'm dealing with, as you say, controversial, some often speculative theories that haven't yet been sort of experimentally confirmed, the proponents, the supporters of those theories, you know, it's almost like a religious dogma sometimes that, you know, my theory is correct, the others are all a load of rubbish. And then you go and talk to someone else and it's the opposite view. I've had to stand back and try and weigh up and assess these different theories as objectively as I can, which helps if I'm not actually working in that particular field. I need to know enough to talk about, to explain it, but not too much that I have some vested interest in promoting a particular idea over any other.
Mm. Well, we could discuss this for some time, I'm sure, but having just started on describing some of those controversies, perhaps this is the right time to hear a little bit more about the ideas in the book and have your presentation, Jim.
Okay, right. So the world according to physics, I have to say, my a colleague of mine at the University of Surrey in the physics department, Justin Reed, who's the head of physics there, he'd helped me a bit. He's an expert on dark matter. So when I was writing stuff about dark matter and how do we know it's out there in the universe, I asked his advice, and of course he helped out. So I gave him a copy of the book when it first came out as a thank you. And he put his thumb, I can't do it here with this technology, but imagine putting your thumb over the word physics. So I said, surely this is a bit, you know, a bit polemical. So maybe it should be called The World According to Jim Al-Khalili, which I quite like. So it's essentially, it's my ode to physics is how I start off the book. It's my love affair with the subject that I've really been obsessed with since I was about 12, 13 years old, when I realized that this is the subject I needed to study if I wanted to find out about, you know, answers to the big questions. Does the universe go on forever? You know, what are atoms made of? What is the nature of time? All these things that I think we all think about, and they're very profound questions, and we may have some views on them. I appreciated that I needed to study physics if I was going to get any sensible answers. So this book is a celebration of physics and just how successful it's been in describing so much of our world, so much of reality over the last few centuries. It's also a book that I champion rational thinking and scientific inquiry, this sense of curiosity about the world, asking questions, coming up with hypotheses, testing them, gathering data, essentially, how we do science. And because we're dealing with some of these very profound ideas, many people who don't have a background in science might say, well, that's one way of seeing the nature of reality. There are other ways. There's meditation, through religion, through other ideologies, through just sitting down and thinking and contemplating and philosophizing and so on. I try and put the case in the book that there's a, and so I should say, not all physicists agree with this particular view, but for me, there's a physical universe out there. There's a reality out there, and therefore there's a truth about how things are. And the job of physics, for me, is to get as close as we can to that truth. We won't know if we have Einstein's theory of relativity. We don't know if that's the whole story. We don't know if that's the whole, nothing else is going to be understood beyond that. But we like to think that as we develop our understanding, we're getting closer and closer to that truth. And the example I use, for example, in the book, something very simple. If I were to drop a ball from a height of 5 meters, then it'll hit the ground after 1 second, as near as damn it. It won't hit the ground after 2 seconds. It won't hit the ground after half a second. Let's assume it's heavy enough. It's not going to sort of be stopped or slowed down by wind resistance. No other ideology, no other way of thinking, no other way of getting to the truth, no amount of meditation or prayer or whatever is going to tell you that a ball dropped from 5 meters will hit the ground after 1 second. Science will tell you that. In fact, Galileo was the first person to give us a simple formula that would allow us to calculate that. So there's something about getting to the truth of reality that science and physics in particular can give that I think no other way of thinking, no other approach can lead us to. I talk about how far away we are from knowing everything we need to know about the physical universe in the book. And it's interesting to highlight this. This is a paper by Stephen Hawking that he wrote back in 1981. I have enlarged that first paragraph so it's readable, where Stephen said, in this article, I want to discuss the possibility that the goal of theoretical physics might be achieved in the not too distant future, say by the end of the century, okay, the end of the 20th century, he means. By this, I mean that we might have a complete, consistent and unified theory of the physical interactions which would describe all possible observations. So what Stephen Hawking is talking about there is what we would call a theory of everything. Sometimes people say it's the one equation you can fit on your t-shirt that will describe, if you unpack it, all physical phenomena, all unifying the forces of the universe and so on. Stephen was optimistic in the early 80s. And I think in the years that followed, physicists became even more optimistic that we were approaching a full understanding of the nature of reality itself. All we had to do was dot some I's and cross some T's. Stephen Hawking was wrong. We were not approaching a theory of everything. We now appreciate, actually, we're probably quite a long way off. And in fact, the same thing happened. There was the same attitude that we're coming to the end of physics at the end of the 19th century. By about 1890, physicists said, okay, look, we've got Newton's laws of equations of motion. We've got his law of gravitation, which is universal. We have electromagnetism, the theory of electric and magnetic fields and the nature of light. We have thermodynamics, the theory of heat and energy. That's pretty much everything. And then in the 1890s, what happens? We discover the electron, the first elementary particle to be discovered. We discover X-rays, radioactivity. No one anticipated this. These were surprises. And then, of course, by 1900, you've got the quantum revolution. Then Einstein comes up with his theories of relativity and so on, and realized we've only just started understanding, some of the nature of reality. It doesn't mean that what we learned in the 19th century was wrong. It's just that we've gone beyond it and understood more. We've got closer to that truth. So if I look back and think over my career, how much have we, what's surprising, what new discoveries have been made that, you know, have really changed the face of physics? And I show two examples here. One is the discovery of the Higgs boson at the Large Hadron Collider back in 2012. And there's a picture of Peter Higgs, one of the people who predicted the existence of the Higgs boson back in the 1960s. He won the Nobel Prize when it was finally confirmed, along with other physicists who'd also been working in the same field. But, you know, the Large Hadron Collider, when it switched on a few years earlier, was big news. And when the Higgs boson was discovered, of course, that was, you know, everyone was talking about it. Everyone's heard of the Higgs boson and the Large Hadron Collider, even if they're not quite sure what it is and what the Large Hadron Collider actually does. Then a few years later was another big headline-grabbing scientific discovery, that of gravitational waves. So these are, I should say, I'm sure everyone watching this will know, because you're all very smart people, that's not to scale, right? So the gravitational waves coming from the collision of two black holes, they're not actually just right next to the Earth. That's just to fit it all in the same picture. But essentially, over 1 billion light years away, in a very distant galaxy, very remote, two black holes have spiraled together and coalesced. And that's such a cataclysmic event in the universe. It sent out so much energy, it was sending out ripples through space itself. Space itself was stretching and squashing, just like dropping a stone in the middle of a pond, and the ripples on the surface of the water will radiate outwards. So too did these ripples from these colliding black holes radiate outwards through space. And 1 billion years later, they washed through the Earth. And we had experiments with instruments sensitive enough to pick up this squashing and stretching of space as these waves of space actually pass through. Brilliant, fantastic, again, headline news. The thing is, neither of these two discoveries, the Higgs boson or gravitational waves, was unexpected. You know, we'd been trying hard to confirm these things, but they were predicted well in advance anyway. Peter Higgs had predicted the existence of the boson 50 years ago. Gravitational waves were predicted very soon after Einstein came up with his general theory of relativity, 100 years ago. So in a sense, if you want to be really sort of not critical, but, you know, sort of mean about these discoveries, they were box-ticking exercises. It would have been more surprising if the Higgs boson hadn't been discovered. So we sort of expected them, and they were discovered, and there they were. In a sense, I guess I've been asked, what is the most surprising thing to come out of the Large Hadron Collider? And I think, and many physicists would agree with me, it's probably the fact that we haven't discovered anything else since the Higgs boson. There was this great promise, the hope that we would see other new particles. Very often people say we're talking about what are called supersymmetric particles, that they will be found, they would confirm a particular mathematical idea called supersymmetry, and that we'd find them at the Large Hadron Collider as we ramped up its energy. And we haven't found them yet. So that in itself, you know, the absence of a discovery is quite surprising. The one unexpected discovery, certainly probably in my lifetime, in my career as a physicist, took place in 1998, and that was the discovery of dark energy. Well, people didn't discover a new form of energy. What astronomers discovered was that the universe is expanding ever more rapidly. Now, we've known since the late 1920s that the universe is getting bigger. Space itself is expanding. It's not everything's flying apart from everything else, and we were all in, you know, we're all in one spot in space, and then we're moving through space. The gaps, the spaces between the galaxies are stretching. We've known this, say, nearly a century now. It was predicted by Einstein's theory of relativity. What we weren't expecting was that the expansion of the universe was speeding up rather than slowing down. We assumed it'd be running out of steam, that the gravity of all the stuff in the universe would be putting the brakes on expansion and slowing it down. Instead, there seems to be something pushing space apart ever more quickly. That's certainly what was discovered. Astronomers were looking at very distant galaxies, and they could measure how far away they were, and they could measure how fast they were moving away from us as the space between them and us stretched. And it told them unequivocally that space was expanding ever more quickly. So what is causing that? Well, we sort of came up with this term, dark energy, as this mysterious force of anti-gravity that's winning the battle against the attraction of gravity. Gravity would try and pull the universe together. Dark energy is pushing everything apart. So no one expected that. And we're still trying to get our heads around exactly what dark energy really is. It's one of the mysteries I talk about in the book, one of the things we've yet to figure out, which is why I say, we're not close to the end of physics yet. There are other things we haven't understood. For example, the nature of the similarly named, but has nothing to do with dark energy, dark matter. Dark matter probably should more correctly be called invisible matter. It's stuff, it's out there in the universe, it holds galaxies together. We believe it was probably necessary for galaxies to form in the first place in the early universe after the Big Bang, and yet we don't know what it's made of. We know it's there, but it's invisible. Light travels straight through it without interacting with it. We know it has gravity, but we don't know what the particles that make it up are. There must be a new kind of particle. So that's a mystery. And there are other mysteries like this that we're still trying to figure out that suggests we have a way to go before we get to the end of the story. One of the things that theoretical physicists have been grappling with is this idea of unifying all our theories. We've discovered that ever since, certainly Isaac Newton, phenomena that seem to be unconnected, the completely different things, physical phenomena, turn out to have a common underlying reason or explanation. The simplest example is Newton, apple falls on his head, whether or not it did, it's a story that he tells. Basically, he realizes that the force or the cause that makes the apple fall to the ground is the same force as that which keeps the moon in orbit around the Earth and the Earth in orbit around the sun. Namely, now we've learned about it at school, and it's obvious. It's the force of gravity. But before Newton, that wasn't obvious. The forces governing objects on Earth that pull the apple down to the ground, why would they have anything to do with the forces governing the heavens? So there was a unifying picture. The force of gravity unifies very different phenomena. And since then, again and again and again, we've found connections. Einstein unifies space and time, says time is the fourth dimension. Maxwell unified electricity and magnetism and said it's all part of the same underlying fundamental force called the electromagnetic force. And light is just an electromagnetic field. Through the 20th century, we've unified a lot of our ideas. We developed quantum mechanics, we developed general relativity, we understood the forces of nature. We've got to the point now, to cut a long story short, we've got to the point now where we have an overarching idea of the world of the very small, something called the standard model of particle physics. It brings together our theories, the mathematics describing the nature of the building blocks of the universe. Then we've got the equivalent standard model of cosmology, which brings together our full understanding of the world of the very large. The difficulty of bringing these two together is that the standard model of particle physics, the building blocks of the very small, are governed by quantum mechanics, the theory of atoms and the particles that make up atoms. Whereas the standard model of cosmology, the theory of the whole universe, that is described by Einstein's general theory of relativity, his theory of gravity. And what we haven't been able to figure out yet is how gravity fits in with quantum mechanics. That's why we talk about the search for a theory of quantum gravity. Now, I mentioned in my chat with Sarah earlier that there are these two rival ideas, two rival candidate theories for quantum gravity, or a theory of everything. And I depict them here as an arm wrestle between two superheroes. So you've got on one side, you've got the string theory advocate. String theory will unify the forces of nature. There's a rival theory that sees reality differently and says, no, string theory is wrong. Loop quantum gravity is what is needed. That's how we have to quantize space and time, quantize Einstein's theory of gravity. They're rival camps, and physicists who work in one area think the other theory is rubbish, and vice versa. One of them may be right. They may both be wrong. I don't think, maybe there's some, one can think possibly, potentially a combination of the two somehow. But the fact is, both of these ideas are highly mathematical, they're highly theoretical, and even physicists are nervous or can be critical about whether they are real science. Because in science, you come up with a theory, you come up with a hypothesis, and you're supposed to then test it and go and do an experiment or make observations, gather data, and see if that theory, that hypothesis is correct. These theories are so abstract and they're so far removed from what we can currently do experimentally, we have no way of checking them. That's why I say we are a long way from a theory of everything, a long way from the end of physics, because our two leading candidates are still very clever maths, essentially, and not much more than that yet. So we have yet to see where we go. Maybe we have to really go back to the drawing board and ask ourselves, what is the nature of the most fundamental concepts of reality? For example, what is space itself? Now you think, it's obvious, space is where stuff happens, right? Space in this room around me is three-dimensional, it's where events take place. Philosophers and scientists have been asking this question for many hundreds of years. For example, does space inside an empty box, let's say a box that's just, it's got a vacuum inside, there's nothing in it, there's no particles, there's nothing. Does it only exist because the box has walls? Does it only exist because it's inside a box? If you remove the walls of the box, does that space still exist? Or was it only defined because it was the gap between the walls? Newton believed that space existed independently of the laws of physics. Newton said, you have to have space, the place where stuff happens, you have to have time ticking by, and then you put in stuff and things happen in it. So space exists. Other thinkers, Aristotle and Descartes, said no, the vacuum inside the box ceases to have any meaning if you remove the walls of the box. So if you remove all the matter and energy from the universe, there would be no universe because there'd be no space. It's only defined because it's got stuff in it. Our current best idea is that of Einstein's general theory of relativity, which would say basically both of those two explanations are partly true. Newton is correct in that space is real. It's not just the gap between the walls of the box. It has a substance. Space can be, I talked about gravitational waves, waves of space itself. Space can be stretched and squeezed and bent. That's what Einstein tells us, so it's real. But on the other hand, space can't exist without matter and energy. Or rather, space-time is what Einstein tells us. Space and time have to be unified. But Einstein's theory of general theory of relativity says that without matter and energy, there will be no gravitational field, and the gravitational field is space-time. It's a really, really profound idea, and I'm not even going to say anything more about it because I would probably go on for much longer than I need to, and I want to wrap up in a couple of minutes. But it's those sorts of ideas that I explore in the book. Let me just say, I'll do give one more example. I should say two more examples, two more things. This is my montage of quantum mechanics. Anyone who's read any popular quantum mechanics will recognize Schrodinger's cat in the box that's dead and alive at the same time. The Greek symbol on the left is the Greek letter psi, which signifies the quantity in the mathematics of quantum mechanics that is important. It's called the wave function. So this is like, it's just a pretty picture while I waffle on. Quantum mechanics is the most powerful theory we have so far in physics, probably in the whole of science. Without quantum mechanics, I wouldn't be talking to you now, because we wouldn't have invented computers. Because quantum mechanics tells us how electrons behave around atoms. It would explain how semiconductors work. It allowed us to build transistors and silicon chips and microchips and so on. So quantum mechanics works. Without it, we wouldn't have the modern world. But at its heart, quantum mechanics is also still struggling to reach some, sort of underlined end of the road. We now understand it, because quantum mechanics doesn't have a single way of explaining what it means. It has a number of what we call interpretations. The narrative, the story, the explanation of what the mathematics is telling us about reality itself. So there's another issue that we still have to be working on. And then finally, another example I talk about is even time itself is something we have yet to find a sort of a common definition for. So here, in the book, I talk about the three pillars of physics: Einstein's theory of relativity, quantum mechanics, and thermodynamics, the theory of heat and energy and work. Each of them gives a different definition for time. General relativity says time is a dimension. It can be bent, it can be stretched. It's part of four-dimensional space-time. Okay, a dimension is like a direction. You can think of, we live in three-dimensional space, right? So I can move forwards, backwards, up and down, left and right. Those are the three mutually right-angle directions I can move in. Time, Einstein says, is a fourth dimension. Quantum mechanics says, no, time isn't a dimension. Time is just a number. You plug it into your equation, you crank the handle, and you can work out what your atom is doing tomorrow. Or crank the handle backwards, you can work out what your atom was doing yesterday. So time is just a number, what we call a parameter. Thermodynamics says, no, it's not a dimension, it's not a number, it's an arrow, specifically pointing from past to future. Quantum mechanics and relativity, quantum mechanics says that everything down at the level of atoms you can run the film forwards and backwards and it's fine, it doesn't break the laws of physics. Thermodynamics says, no, time moves from past to future. It's a direction, it's an arrow, in a way that the other theories don't really explain. So even something as fundamental as the nature of time itself, we are still struggling with. That's why I think it's exciting. The time we're living in now in fundamental physics is exciting, because we are starting to appreciate that there's a lot more we need to understand. And that's good. If we understood everything and had all the answers, it would be a very boring place. Okay, some areas of science we'd like to know more about because we need to know more. But when it comes to theoretical physics, some of these fundamental issues, I enjoy the deep thinking, the trying to figure out what it all means. And I want to get to the answers, but at the same time, it's like anticipating Christmas. Once you've opened your Christmas presents, it's never quite as exciting as it was just before you've opened them up. And I think I will stop there, because I want to give you guys all a chance to ask me some questions.
Fantastic. Thank you, Jim. Yeah, what very stimulating talk. And we can see from the questions that you have indeed been stimulating lots of questions.
I can see the number.
Yep. And I think there's a lot of questions about what you've been talking about the theoretical physics. And there's quite a few questions about studying physics and slightly more personal questions. And I'm going to try and start with the physicsy ones, and then get on to the other ones. And forgive me, audience, I'm trying to collect things and I may miss some, and they won't come out in a coherent order, Jim. So given that you've just been talking about quantum mechanics and about the challenges of interpreting it, there's a question here from Clovis, who says, how different will the world be if quantum mechanics is fully understood?
Well, certainly we are hoping to develop a lot of technologies that are based on the more mysterious aspects of quantum mechanics, what we call the more counterintuitive areas of quantum mechanics. So without quantum mechanics, we wouldn't have modern electronics. So a lot of our modern technology is only possible. You know, your smartphone, your laptop wouldn't exist if we didn't have an understanding of quantum mechanics. Having an interpretation of it, I think, is going to be important if we are going to resolve some of the big mysteries in physics. I think it's not just an issue of philosophy. It's not just a navel gazing. Well, quantum mechanics works. Who cares whether there are parallel universes or signals traveling back in time, whatever. No, I think getting the right explanation of quantum mechanics is necessary. So if by a full understanding of quantum mechanics, it's finding the right interpretation, then I think that will certainly lead to advances in physics. But, you know, we are also exploring aspects of quantum mechanics to develop new technologies, to develop quantum computers, quantum cryptography, quantum sensors, quantum teleportation. You know, those are very exotic things that I think are going to become part of our modern world in the 21st century that do require further study of quantum mechanics.
Can I leap in just there, Jim, because there's two questions. So you might want just to expand on a couple of things you just said. There was one question, Uli Schmidt has asked, how close are we to quantum technology, computers becoming mainstream? And somebody else has asked, how viable is teleportation? And do you think we will be able to teleport humans one day? So you've just touched on two things.
Okay, so very briefly, quantum computing, people may have heard in the news last year, I think, you know, there's certainly companies like Google and IBM are in competition with each other to try and build the first quantum computer. And things like, you know, achieving what's called quantum supremacy. Quantum computers are going to be with us. I don't think they're ready yet, but certainly in the next decade or two, I think quantum computers are going to be coming online. Whether it means you're going to be able to order one and have it sitting on your desk at home, I don't know. Quantum computers aren't going to replace every computer we have now, which is called a classical computer, but they will be able to perform tasks much more efficiently, much more quickly than anything we have at the moment, however big and powerful a supercomputer it is. So they will, I would predict 10 to 20 years, I say, before they become commonplace. Quantum teleportation, yeah, we should try and distinguish between what we call quantum teleportation and your Star Trek, you know, transporter room, moving humans from one place to the other. We can certainly quantum teleport at the quantum scale, maybe, you know, one photon of light over here, another photon over there. You need particles to be what are called quantum entangled, but what you're transporting is quantum information. So to teleport a human made of trillions and trillions of atoms, the amount of information that a human would contain is so vast that it's way beyond any possible feasible technology that we could conceive of now. Now, maybe in 1,000 years from now, who knows? You know, what we would regard now as magic will be commonplace. But we're a long, long way from being able to teleport anything beyond a few subatomic particles at a time.
Some of the physics is actually already there.
Yes, that's true, and sometimes, I mean, certainly the Chinese are developing technologies with satellites sending entangled photons down to Earth and using it as a form of quantum encryption. There's very exciting stuff going on, but a long way from teleporting humans from one place to another.
And now perhaps a little bit back to what you were originally talking about. There's a question from Ian Lewis who asks, what is your assessment of the many worlds theory of quantum mechanics? Question I'm sure you've been asked before, Jim.
I have been asked before. It's interesting. I was on an episode of the Infinite Monkey Cage with Brian Cox and Robin Ince a few months ago, and one of the very sort of enthusiastic advocates of many worlds theory, Sean Carroll, physicist at Caltech and a good friend of mine, was on there, and I was invited on to give the opposing argument to the case against many worlds. I'm agnostic about it. I don't think it's rubbish. I don't think it's wrong. I just find, so this is the idea that, faced with a choice, if an electron is faced with a choice of going this way or that way, then both options are realized in one reality, one universe, it goes one way, another universe, it goes the other. We only ever see it going one way or the other, but that's because we inhabit one or other of those universes. So every time in the quantum world something's faced with a choice, whole of reality splits, and so you have a near infinite number of realities of universes. I find that metaphysically far too expensive. I'd rather, this is not the way physicists should work, and I believe there's only one universe, but I'm not a fan of many worlds, but I think more to the point, just because it's simple, or just because it doesn't have much added baggage or further assumptions, doesn't mean it's correct. I can see the appeal, but I find it hard to swallow. But that's, as I say, that's not the way you make decisions in physics. We haven't yet developed an experiment that can discriminate between the different ways of explaining what's going on in the quantum world. Many worlds theory is just one of half a dozen or more pretty respectable ways of explaining everything we see in quantum mechanics. They all agree with each other in terms of what they predict, but they all tell different stories about how stuff is happening.
So as you're straying there into the highly theoretical, and you touched a little bit on, sometimes that makes physicists feel a little bit uncomfortable. And there's a question here from Katya who says, do you believe that every discipline is fundamentally applied maths? Which maybe touches on this a little bit.
No, I don't think, applied maths and then that becomes physics, and physics underpins the whole of chemistry, and chemistry underpins the whole of biology, and biology underpins the whole of psychology, and psychology underpins all the social sciences and so on. No, I think every discipline applies at a particular scale, and we would say in physics, and it doesn't make sense to try. The simplest example, even within physics itself, I know that my washing machine ultimately is made of quarks and electrons. I don't need to study the standard model of particle physics to fix my washing machine if it breaks. Pointless. Right? So I think, and again with science, there are different ways of doing science. There are different types of observations. There are different phenomena. It's not completely reductionist, psychology, biology, chemistry, physics, and maths is the purest, and maths underpins it all. I mean, I'm sure you have as well, Sarah. We rib our chemist colleagues by saying, well, chemistry is just a branch of physics, but we sort of know it's not. It's another field entirely.
We have to acknowledge that. Yeah. Now that leads us on to another. There's quite a few questions about biology and quantum biology, but the first one's more about biology from Rosemary, who says, how near might physics be to helping improve the basis of biology and the development of new medical therapies? This comes back to your sort of applications and the usefulness of physics.
Yeah, I mean, historically, physicists have been rather arrogant in terms of how much they can help other areas of science. But certainly we are seeing increasingly now interdisciplinary research areas. So things like artificial intelligence, genetic engineering, robotics, lots of areas need expertise and seem to be advancing because there's a collaboration between physicists, chemists, biologists, computer scientists, mathematicians, engineers. So yes, I mean, there's an absolutely huge and vibrant area called biophysics, the physics of biological systems. And the boundaries are blurred. Someone who's a biophysicist or physical biologist, they don't belong in one camp or the other. They're not physicists invading the world of biology or vice versa. It's just, there's an overlap between these disciplines. And I think physics and there's biochemistry as well, where chemists work with biologists. These are areas that are perfectly valid and established areas in their own right.
So there's also a few people have obviously heard you talking about quantum biology in the past. So there's one question from Katya again, who says, your quantum biology TED talk is one of my favorites. Have there been any advances made since you did that talk that you find particularly interesting?
I'd say when I gave that talk, I don't know, 5-6 years, I can't remember now when I gave it, the TED talks, they're so prescriptive, and they give you so much advice as what to do and how to. I had to stand rooted to the spot. If you watch it for 30 minutes, my feet are glued to the ground and I just turn around. But good, I'm glad Kathy enjoyed it. Well, certainly from my perspective, what has changed in the field of quantum biology. So quantum biology is still a speculative new area of science. It's looking for particular examples within molecular biology, so down at the cellular level, not sort of organism as a whole, but within cells, down at the level of molecules. Are there processes that only work because they get a helping hand from the rules of quantum mechanics, which seems perfectly valid? And so that's what I talked about in my TED talk. Since then, we've now got a research center at Surrey looking into quantum biology. It's a doctoral training center. We're taking another cohort of half a dozen more PhD students later this year. So I've got very much more involved in research into quantum biology. I started off my career, as you will know, Sarah, as a nuclear physicist, studying the atomic nucleus. More recently, I've been looking at some of these ideas in quantum biology. There haven't been experimental breakthroughs beyond what I talked about in my TED talk. So there have been examples that, some aspects of photosynthesis suggest that photons, particles of light, behave quantum mechanically, moving in multiple directions at once. The idea that enzymes can move particles around within biomolecules through what's called quantum tunneling. The idea that a particle can move through an energy barrier that it has no right to get through, but because of quantum mechanics, because it behaves like a wave, it can sort of leak through. So there've been experimental results that suggest quantum behavior. Most of the advances that have been done have been more on the theoretical side, modeling some of these examples. So we have chemists, biologists, and physicists working together, modeling, for example, how mutations take place in DNA, how a single hydrogen atom, or the nucleus of a hydrogen atom, a single proton, can quantum tunnel from one strand of DNA to the other in a way that, without quantum mechanics, it shouldn't be able to do. But I say, because it's a new field and it's quite tough going, it's hard work, progress is slow at the moment. There haven't been any sort of huge major breakthroughs, no Nobel Prizes just yet.
Well, but this time. Well, that will depend on there being some experimental discoveries, I guess.
But it's hard, that's why physicists, people say to me, why would you go and apply your ideas of physics in the messy world of biology? In a physics lab, you can control stuff. You can do it near 0 degrees temperature. You can do your experiments in a vacuum. You can bounce lasers off mirrors very precisely. You can shield it from its surrounding environment. In the messy world of biology, inside a living cell where you've got thousands of chemical reactions and all sorts of things going on, how can you pick out a particular mechanism and say, well, that happened quantum mechanically, even though it's surrounded by it or the other gump? So it's very difficult to design an experiment that can isolate what is actually going on at the quantum level.
Yeah, the complexities of life and biological systems are really something different. And I should also say that there was Harry also said how much he enjoyed your book Life on the Edge, and was also asking about quantum biology since the publication. So I think you've answered the question.
Same,
But
same answer, Harry. Yeah.
So there was a question here. I'm just going to try and find which related to what you were just saying. It was about consciousness, and I'm not going to be able to find it now. But it was basically about whether or not physics would be able to shed any light on consciousness. I'm pretty sure that's what the question was. I'm sure it was phrased better than that, but that was the... Yes, well, it was from Charlotte, and it says, how does physics attempt to explain consciousness or self-awareness? So just as you were touching on that, I wondered if you had any perspective.
Well, I think the honest, the modest answer is no. Physicists aren't in a position to explain something beyond what neuroscientists and psychologists and are trying to study in terms of what goes on inside the brain. Certainly, I think that the connection, and a lot of people ask me this, the connection when you talk about quantum biology, the big thing they come up with, okay, so quantum mechanics might explain consciousness. I doubt that very much. I mean, there's a very famous example a few decades ago. Roger Penrose and Stuart Hameroff produced this idea that consciousness is switched on because of quantum effects in the brain inside these proteins called tubulin. But really, yes, quantum mechanics is mysterious. Yes, consciousness is mysterious. That does not necessarily mean the two are connected. Okay, so it's unlikely that quantum mechanics explains consciousness. It might do, but whoa, let's walk before we can run. If we jump straight to
quantum mechanics,
and if you do say, quantum consciousness is quantum, before you know it, you've got people appealing to quantum mechanics to explain all sorts of nonsense, telepathy, homeopathy, etc. By which, in case anyone didn't hear me, telepathy, homeopathy, nonsense. Anyway, cue Twitter storm.
Yeah, so there are just so many questions here, but I think there's quite a few asking about, why you went into physics. And let me just ask you a few of these. I'll read a few of these out, and then we can answer them together. There's one asking about flavors of ice cream. What's your favorite flavor of ice cream, Jim?
Salted caramel.
There we go. That was an easy one. We're up to quite a few questions here. Just trying to find the names of the people asking, but yeah, so there's a couple of people. George Dixon is asking, is studying university physics as exciting as physics seems to be when we watch seminars and talks such as these? There are other questions about, why did you go into studying physics, and the questions along those lines. So
I mean, I certainly, so I got interested in physics in my early teens. I obviously at that time, and to some extent still now, I still had ambitions to be playing for Leeds United, and being a rock star and an inventor or whatever it is that I want to be. But for me, and it was a physics teacher, as is often the case, who inspired me. But for me, I realized that physics was a subject that I would have to study if I wanted to know about the nature of time. My dad had mentioned something called quantum this or that, and I really wanted to know what it was. How are stars made? Does the universe go on forever? Those sorts of big questions. So right from the age of 13 or 14, that was it. I knew I wanted to study physics, A-levels, go on to university to do it. When I got to university, I have to say, I really became passionate with physics only halfway through my degree. I think my first and second year, I struggled through the core course on quantum mechanics in my second year. I did a year out, professional training year, so a year in industry, in a job that I didn't really enjoy that much. But I did spend that time reading the biographies of some of the great physicists, my hero, Feynman and Bohr and Einstein and Dirac and so on. And that just got me so inspired, finding out about how these people came up with the ideas, particularly the founders of quantum mechanics, so that in the 1920s. And I went back into my final year just fired up, shiver down the spine when some equation is derived on the board, a complete geek. And after that, that was it. I knew I wanted to stay studying physics, go on to a PhD and stay in academia. But it wasn't, I was interested in it, but it wasn't until halfway through my degree that I guess fell in love with the subject.
So interesting that you brought in there, it was something about the lives of the physicists and the story that was around it, which is what, you've been doing a lot in Life Scientific, but also in a lot of your, your public engagement. And it leads me on to a question that I wanted to ask, which I think it speaks very much to what you've just been saying. Is you talk a lot in the book about thinking like a physicist, and asking the right questions, and also the scientific method. But of course, you've got to ask the right question in order to, if you don't ask the question, you don't always get the new
don't
answer.
Expect the answer.
Yeah. So how do we teach that, or how should we teach that thinking like a physicist bit, which is so much part of the scientist and so much part of the physicist?
Yeah, I mean, I preferred physics to, and this is just a personal view, I preferred physics to chemistry and biology, because in chemistry and biology, you had to remember stuff. And I didn't want to remember stuff. I wanted to figure things out. So for me, physics is puzzle solving. It's a mystery. There's a way of solving it. And when you realize and you get to a certain level in physics, probably in A level, I guess you'd start doing it this way, you realize that using the language of mathematics helps you find those answers. You realize that you can design experiments in a lab, that you force nature, you prize out of nature how things are, how things work. And then you go to your theory and you see the mathematics predicts that's what you should see. And you think, whoa, the world, the nature, the universe seems to be really good at maths. And that understanding, I don't think is explained. It's not taught to physicists or budding physicists. The other thing I think is, in terms of you mentioned asking the right questions. If one thing I learned reading the philosophy, the biographies of the founding fathers of modern physics, is that they were all very deeply steeped in philosophy. They understood some issues in philosophy. Some physicists, regrettably these days, talk about philosophy being a dead subject. That physicists don't need philosophy. Philosophy helps us organize our brains, helps us organize the questions, and asking the right questions. So physicists will try and look for the answers, but very, very often you need philosophers to help us pose the right questions. So I think a bit more philosophy taught within physics would also be very helpful.
Yeah, I think that's a wonderful insight, and it's a wonderful way to come to a close. And unfortunately, we are going to have to come to a close, and there are so many more questions on this list that we could have asked. And Jim, you in very typically physicist modesty, you described it being a bit like a headache when you've got something that's hard to understand, and then you gave it away just a few moments ago because you described it as a fizz of excitement. And I think that's much more like it. And reading your book, you get those moments when you're trying to describe, the unimaginable, which I think was a phrase you use. And that's when your brain does that fizz thing, when you think, wow, this is really exciting. And we've had an insight into that this evening from your descriptions and the answers to your questions. And you've certainly made me smile about your descriptions about what it is to be a physicist. And there's a lot more in the book for people to read as well. But thank you for stimulating us, and thank you for answering the questions so beautifully. So thank you.
My pleasure, Terence. Thank you very much, and I hope everyone enjoyed it. It's been really fun.
So to the audience, thank you very much for all your questions. There seem to be I think we're up to 113, and I'm very, very sorry that we haven't been able to answer them all during the broadcast. If you'd like to purchase a copy of the book, as in I have in my hand, The World According to Physics, it's available from our partner bookseller, Fox Lane Books. And for more information, you can go onto the festival website or directly to foxlanebooks.co.uk stroke Festival of Ideas. And if you want to hear all this again, the recording of the event will be available on the festival YouTube channel, which can be accessed from the Watch Again section of the festival website, if you just give it a couple of days until it appears. We hope you'll continue to be engaged with the Festival of Ideas, York Festival of Ideas. Check out the website, yorkfestivalofideas.com, for full details of all the events, both past and upcoming. And we'd love to hear what you think about the events, and you can continue the conversation using the hashtag York Ideas. So thank you for joining us. Thank you again, Jim, and good night.
Bye-bye.